Hi guys, welcome back. Mr. Smith here. As we've seen in class, radioactive elements emit radiation when they feel like it. You can't track any radioactive element and know exactly how many particles it's going to emit per given time because we're not privy to what's going on inside the nucleus. It's just too small of a space, even now with the most advanced physics we have. But we can use statistics. And what I want to do is walk you through in this deck the first part of how we study radioactive statistics and use those to look at radioactive decay. So to begin with, I've got a sample example of a radioactive nucleus, and it's going to spit out, or it's not going to spit out, a radiation anytime it feels like it. Could spit out a gamma ray, that would be electromagnetic energy. It could spit out an alpha or a beta particle. However, what's going to happen is if delta N is the number of nuclei that go pop and emit a radiation, the number of nuclei that we see going pop is going to have to do with how many nuclei there are in the sample. So that should make common sense. The second thing is the amount of radiation counts we count should also depend on how long we count for. So what I've done is just make a simple graph where I've got the number of counts we get in a detector, and N is the number of nuclei we have in our sample. Delta T is how long we want to count for. And what we're going to find is that for every amount of nuclei and delta T that goes on, we're going to get some kind of random scattery pattern. But what's going to happen is that those random scatter lines are really going to follow a nice straight trajectory, because when we have a lot of nuclei, which we always do, we're going to get some pretty consistent behavior. So what that means is that the number of nuclei we're going to see in our detector is going to, well, before I get to an equal sign, let me show you. It's going to be proportional to the number of nuclei I start out with and the change in time. And then what we do to turn it into a linear relationship is just invent a thing called an empirical constant. So empirical just means based on experiment. So what we're going to do is measure this number called lambda, which is a unique number for each element, and all it has to do with is how likely is an element to go pop per given time. Okay, so we're going to go talk about our samples right now, and I'll show you how it works in real life. So these are the ones that you've got experience with. Our red source is polonium-210 and has a half-life of 138 days. So you probably know by now that means that the amount of the sample decays by half every 138 days. So not surprisingly, we have to replace these ones after a little while. Strontium-90 has a half-life of 29 years. Those will go for a good long time, and I've never had to replace one of them. And gamma source has a half-life of 5.3. That'd be kind of fun to have a drag race between some of the ones in the sets that we have in our lab and see if the ones that are older are any different than the ones that are new. So what I wanted to show you, very simply, is how to get a lambda. So here's the formula straight away. It says that lambda equals 0.693, a number we'll explain later, divided by t1/2. So all you have to do is just plug in like a monkey, right, without paying attention to labels, right, like we always do, and you're going to get 0.693 over 138 days. And what do we get? 0.005 days to the -1, right? Except you're going to remember, I was only kidding. I never want to plug in like a monkey, and I never want to be unaware of labels. Why? Because days to the -1 would give us an activity in how many counts per day we're going to get. And very often what happens in these problems is you want to figure out the decay constant in terms of seconds. So what I'll often have to do is a little first step. And this is usually the first thing that I do, is I'll take the half-life and actually convert that into seconds. So I'm going to go 24 hours per day. It's an oldie and a goodie, and I know you've done these conversions before, but they're really important to pay attention to so that you get units that are really useful to you. So what I do when I work all through this is I get the decay, the half-life for polonium-210 is 1.19 times 10 to the 7 seconds. And then if I go through the work of getting the lambda, the decay constant for that, still 0.693 divided by t1/2, but obviously the number is going to be quite a bit different. So I'm going to go ahead and plug all that in, and I get the decay constant for polonium-210 is 5.81 times 10 to the -8 seconds to the -1. Okay, so file that idea away. We're going to use that repeatedly. Now let's jump into an actual problem. What we want to do with this one is go and figure out if we had a milligram. Is that a lot of polonium-210? We're going to find out. What we have to do is just figure out the activity of it. So I've got my formula that I've already written down. The number of nuclei that are going to go pop is going to equal lambda times the number of nuclei times delta T. What we're going to do out of that formula is make a second formula. And all I do is slide my delta T underneath. And this right here is called the activity of the sample. This is how many nuclei per unit time are going to be emitted. This is the key in the problem. When they say find the activity in counts per second, that's going to be the cue to you to say, okay, I've got to figure out lambda in a particular unit. So when they say counts per second, I did the right thing and I set you up for success here. What we're going to do is just follow this formula and go and get delta N over delta T as the thing we're after. It's the activity of the sample. And it simply is going to equal lambda, the number I figured out, times N, the number of nuclei. Okay, so what I have to do first then is to take 1 milligram, 1 times 10 to the minus 3 grams of polonium-210, and turn that into nuclei. So what I do, same thing every time, is I reach back into the vault of chemistry knowledge and I remember that there's an Avogadro's number of everything in a mole. So that's 6 times 10 to the 23rd nuclei inside of 210 grams of polonium-210, right? So I use that to get the number of nuclei. So easy enough. So the number of nuclei turns out to be 1.26 times 10 to the 23 nuclei in my sample. Okay? And then I just go ahead and follow through. So 1.26 times 10 to the 23 nuclei times the lambda, which I just figured out. So the lambda was equal to 5.81 times 10 to the negative 8 seconds to the minus 1. And now track the labels, okay? You can do the orders of 10 and plug this into your calculator, and I get 7.32 times 10 to the 15. And that's going to be nuclei per second. You see that? Okay, so nuclei times seconds to the minus 1. So that should make sense. That's how many counts or radiation are going to be emitted per second. 7.32 times 10 to the 15 radiations per second. Okay, so that's our polonium-210 source. We're going to work through one more, and then I'll set you loose, and I want you to do the third one on your own. Let's go ahead and check out our strontium-90 source. And I said this one was the one that doesn't run out of juice very quickly. So first thing we're going to always do is read the question. If they want counts per second, our first job is to take the T1 half and turn that into seconds. So I have 29 years, and I'm going to just do what I need to do. So 365 days in a year, etc. So 24 hours per day. And then I'm a big fan of this right now, the 3,600 seconds per hour. And I go and get my T1 half. So that turns out to be a lot, 9.25 times 10 to the 8 seconds for the T1 half, okay? Step 2, we knew that we wanted the lambda in seconds somehow because of the framing of the problem. So lambda is just going to be 0.693 over the T1 half, this guy, 9.25 times 10 to the 8 seconds. And that gives us a little decay constant of 7.58 times 10 to the negative 10 seconds to the minus 1. Okay, so we're ready to roll there. Step 2, pretty straightforward. Just get the number of nuclei, and that depends on the size of the sample. So if we have the same size sample, it's going to be 1 milligram, so 1 times 10 to the minus 3 grams of strontium-90, and I'll just keep that in mind. I didn't write it, but I'll keep it in mind. And that's going to be turned into nuclei by Avogadro's number. Nuclei are the number of nuclei inside of 90 grams of strontium-90. Again, the top and the bottom both equal 1 mole of strontium-90. That's why I can get away with that step, and it's such a nice conversion. So I get 6.69 times 10 to the 18 nuclei in my sample. Okay, fair enough. Now step 3, this is the easy part. The activity of the sample is the number that go pop per unit time, and that's just going to be equal to lambda times n. So I put step 1 and step 2 together. Pretty easy, 7.58 times 10 to the negative 10 seconds to the minus 1. And then times 0.669 times 10 to the 18 nuclei in my sample. And that all works out to, let's see, 5.07 times 10 to the 9 counts per second, or nuclei per second, that we're going to see decaying. So that sounds like a lot, right? 5 billion counts per second. A milligram of radioactive stuff is actually a really lot. But go and compare something, right? Compare that to 7.32 times 10 to the 15. So this right here is like 1,000,000 times more active. So think about it. If you have a long half-life, it means the radioactive thing lasts for a long time, but per nuclei, the chances of it exploding or emitting a radiation are lower. So what are your most dangerous radioactive materials? It's actually the ones with a really short half-life, depending on what they do. So we'll get really into that. It's a fascinating conversation. So what I want you to do is check out this one. Pause the deck and go and work this one on your own and use our 2 formulas here. And then when you unpause it, I'll show you the last slide where I've got it all worked out. Okay, and we're back. So here are your answers. Hope this all worked out for you. Bring your questions to class. I'll look forward to talking to you real soon. Take care and have a great one. Bye-bye.